Today's lecture is on basics of particle motion, and I hope this topic is little special to all of us because we're going to you're going to enter into the shoes of an atom and see how it behaves in a system. So let's get started. So before diving into the slides, let us take a moment to recapitulate what we have discussed in the last session. So we in the last session basically have tried to know answers for these three questions. What is MD? Why do we need MD? And how do we implement MD? And if you could quickly recollect or recall, molecular dynamics, or in short MD, is a deterministic tool used for analyzing the physical movement of particles. And the last session, I referred atoms and molecules whenever I use the word particles. But we did not always limit the particles to only such small objects or particles or entities. These days, often the molecular dynamic models are quite extensively used for studying the explosion effects of a torpedo or the explosion effects of different bombs used in the war. So this is not just limited to a small system. We can also extend the similar techniques to study much larger and much bigger systems altogether. So we can also sometimes use this tool, the techniques of this tool, in understanding the galaxies and celestial systems and also things like that. So multi-dynamic system is basically a deterministic tool, so which is used for the analyzing of physical movement of particles. And in our attempts to understand why do we need MD simulations, we have noticed the gap between continuum models and quantum models. So leaving the mesoscale studies untended, and that is when we have also acknowledged that having control over materials properties at mesoscale can revolutionize several domains, including materials and manufacturing sciences. So thus a tool like MD, which caters to the mesoscale modeling, can be of great hope to revolutionize the materials that we have in our hand right now. And we can also have a very revolutionary um, extension of the existing materials. We can really enter into mesoscale and operate the parameters there. And the last question that we have attempted to answer in the previous session was how do we implement molecular dynamic simulations? I told you that most of my consequent lectures will be focused on this third question, and I have given you a very basic idea of a basic algorithm of molecular dynamic simulations. And in this lecture, I would like to take up from there and continue with the very algorithm of molecular dynamic simulations. So we'll study a little about molecular dynamic simulations and the elements used within this algorithm to some extent. So let us start with one particle system. So first of all, let us observe and study the behavior of single particle in our system. In order to do so, we create a simulation box. So this is the simulation box that I've created. And the dimension of the simulation box is like length L and height H. So these coordinates, you can fix them by yourself based on your requirement. I have taken it from 0 to L and 0 to H along X and Y directions respectively. So the very first thing that I will be doing for simulating a one particle system is create a simulation box. So this is my system. And next thing I'll be doing is I'll create a particle inside the system. So when I say I create a particle inside the system, I mean that the value of X should be in the range of 0 to L and the value of Y should be in the range of 0 to H. That is quite implicit. And I'll also give some initial velocity to this particle. So the velocity will have X and Y components because this is basically a 2D kind of simulation. So I'll give velocity to this particle, and after time step dt, the particle would reach to a new position because of the imposed velocity. So take a note of this new position, and if we let it move for another time step, after another dt time lapse, this would reach from here to here because of the imposed velocity to the particle. And as you have rightly guessed, if I just let it go for another time step, it would basically it would basically leave the system, right? So if it leaves the system, we'll fall short of particles inside our simulation box, and our study on system becomes meaningless whenever the particles escapes from the system. So we should think of a means to keep the particles inside our system. And by saying so, I'm saying that we should think of ways to deal with particles as they approach the boundary of our system. And we call these particular constraints as boundary conditions. So have here if we observe, we can find two basic ways of saving the particle from escaping the system. The first one is bouncing the particle back into the system whenever it reaches to the boundary. So I have not let the particle to go out from here. Instead, I have deflected the particle to bounce it back into the system. And the second way is to allow this particle to escape and bring in a new particle, a substitutory particle, into the system in the place of particle that we have lost. So whenever we are feeling that we are losing a particle from our system, we let it go into outer space and we allow another particle to take its place in our system. And this particular application is called periodic boundary condition. So we have like a vague idea of how we deal with particles when they reach to the very boundary of our system. So one is reflective boundary condition and the other is periodic boundary condition. And now I would like to give you an activity on this one particle system. But let me first give you more details about these boundary conditions and so that we can come back onto this one particle system again and see what exactly you're supposed to do in this one particle system's simulation. So I was talking about these boundary conditions, right? Reflective boundary condition and periodic boundary condition. So over to the left, you could see a system which contains 6 particles in it, right? And these 6 particles, I want to impose reflective boundary condition into this particular system boundary and see how the particles would behave under this implication of reflective boundary conditions at the boundaries. So I would let the animation to start now. So I want you to observe these particles as they approach the walls of simulation box. Yes, they were bouncing back into the system when they reached boundary. You might have also observed that these particles were changing the direction of their velocity after hitting the wall, and that kind of puts them back into the system. So basically, this system has all 6 particles in it at any point of our study or at any point of our simulation. So we have retained all the particles within the system, no matter how fast they are moving or how slow they are moving or where exactly they are moving. So whenever they hit the wall or whenever they approach the wall, we put them back into the system by bouncing the particle against the wall. So this is a reflective boundary condition. So I would call it as RBC in short from now on. And over to the right, you could see periodic boundary condition. So I have taken a smaller system now, and you could count the number of particles to be 7 here initially. So these 7 particles are within the system now, and I want you to taste these particles very carefully after I start the animation. Yeah, to make this more challenging, I have copied the images of this central system all around the central system. So all these are exact duplicates, exact identicals of the central system, but I want you to only observe whatever is happening inside this central system once I start the animation. Yeah, the particles were moving out from the central system. But you might have also observed that whenever some particles, like if you observe the blue particles, they were moving onto the topmost image, and subsequently the particles from the bottom image were coming into the system. You can also observe it for any other particles. All the yellow particles were contained inside the system, sorry. All the yellow particles were contained inside the system even after the simulation is done. But if you observe the red particles, these red particles from the central system is trying to go towards this direction. And the particle from this image has crept into our system. Similarly, the green one, if you observe, yeah. So at the start, we have 7 particles when we started the simulation. And even towards the end, we could retain all the 7 particles without actually restricting any of their motions at the boundary. So we have allowed the particles to cross the boundary to whatever direction they want to go, whatever way they want to go. We have actually not restricted them at the boundaries, but still we could retain all the 7 particles in our system. So this implementation, we call it as periodic boundary condition. And you might have also observed this here. Unlike in reflective boundary condition, when particle hits the boundary, it used to deflect and change its direction of velocity, right? So velocity of this particle is along this direction initially, but after it reflects at the wall, it kind of changes its velocity by changing its direction to the downward side. But over here, the particles were always free to carry out their velocities in their initial directions. They were not changing their directions for anyone's sake. So this is what I want you to observe in these boundary conditions, in these both kinds of boundary conditions. But before I take you to the next slide and talk about this one particle simulation thing, I want you to think on these particular two boundary conditions, RBC and PBC implementations for a moment. In reflective boundary conditions, our system has the effect of boundary felt in the simulation. See, whenever you hit the particle, you're bouncing it back. You could clearly evidence the effect of boundary. The influence of boundary is very much felt in our simulation. So when we take RBC, the boundary effects are there, which means that if you have a bigger system, say for example, if this size is enlarged to a bigger size, and these particles were moving in this simulation block, we'll be requiring more number of particles to reduce the effect of the boundary condition or this effect of boundary. If you have fewer number of particles, each and every particle would influence some effect from the boundary, and they would change as per the effects or as per the implications of the boundary. So if you have large number of particles, only few of them would interact with the boundary and other particles would interact among themselves, and that would leave us in a system which is free from the boundary effects. So when you look at the periodic boundary condition, that is what is exactly happening. We don't feel any particle being restricted by the boundary. So the very motion of these particles would be free from the boundary effects, which is to say that if you have a reflective kind of boundary condition for your simulation box, for your system, then you'll be requiring huge number of particles to counteract or to oppose the boundary effect induced into your simulations. Whereas if you have periodic boundary condition, even the fewer particles that you have taken, handful of particles that you have taken in the system, are sufficiently enough to get your system away from this boundary effects. So this system is kind of imitating whatever is happening in a very huge quantities of system. So this is not a behavior of a system when it is very small. So actually huge quantities of liquids will have this kind of behavior. So you don't have the limitation of boundaries being entering into your simulation results when you take periodic boundary conditions. So you can kind of simulate a very large system using a very fewer particles in your hand. Right. So with this, we'll go to the single particle simulation that I'm talking about. And this is what I want you to do as a task. I'm getting few queries from your end. I'll take time to answer all of them at once towards the end of the lecture so that you would not miss the continuity in all these slides. And I'm almost there. So within a couple of minutes, I'll take up your questions. Hope that is fine with you. So now I want you to actually code, or maybe you can use whatever programming language that you are comfortable with to do this task. Or if you want, you can also do some sort of hand calculations if you're like planning to do only few iterations. So whatever you plan to do, you can actually do that and get this simulation done for a single particle simulation box. So what all you have to do is you have to create a system with some particular box size. I have taken boxes as L and H, length and height, x and y directions. So the minimum value that I want to assign my box along x direction is 0 and the maximum is 10. Similarly for y also, I have the minimum and maximum value is 10. So this is the very first step that I have to do in order to create that simulation. And the second thing I need to do is initiate the particle with some position and velocity values. So these values that you could see here that were highlighted in red are those particular initial values I've submitted to the system. Except for these values, none of the other values were given from my end. The system is trying to take these particular pure initial inputs and carry out entire simulation by itself based on this particular logic. So once I have the initial position and velocity at time step t equal to 0, I would like to find the position of particle after time t equal to 1. So for now, let us not really bother about the units of this time step or units of whatever dimensions that whatever sizes we are taking up here. because in my next lectures I'm planning to take up these units and other session on units in other dimensions. So over there, we'll have a clear discussion on what kind of units we are supposed to handle in the simulations. But for now, since this is a very elementary simulation, I want you to just focus on the numerical values rather than units. So at t equal to 1, I want to find out the position of this particle. And this is a very simple relation that you have to relate between the positions at this time step to the next time step. So x equal to x at new time step equal to x at old time step, that's vx at old time step times time step value. So that makes my x at t equal to 1 equal to 10 and y at t equal to 1 equal to 5. The moment I have the values of x and y, I'll have to check whether these coordinates of the particle correspond to a position inside the box or outside the box. So if it is trying to leave the box, I have to bring it back if I want to implement reflective boundary conditions, or I can let it go out from my box, but still I have to compensate it with other particle if I'm planning to do a periodic boundary condition to my system. So let me first only concentrate on this particular part. Once we finish this flowchart, we'll see what the other values in the table actually mean to us. So I can calculate the values of x and y at times t equal to 1. So once I get these values, I'll check for x if it is less than x minimum or not, y if it is less than y minimum or not. If it is less, which means it has left the particle has left my system from left side or from the bottom side. And then I have to use some kind of boundary condition. And after correcting this particle position using some boundary condition, I can print the position. But in my case, it is not crossing the system's boundary. So this is no, and I'll check whether the particle has more length in x when compared to the box length or more height in y when compared to the box height. So even in this case, it is not crossing the boundary. So I can simply ignore this as well and I can print the position. So whatever positions I got at t equal to 1 are safe for my particle and system. And I carry it forward. So after printing the positions, I would check the value of number of iterations. If the number of iterations I'm planning to do is 6, and I'm still in the first iteration, so I would call this loop to restart, and then I would again update the position of the particle. So once I update the position of the particle, I have now found that the position of particle, the x coordinate is being 12 here. 12 obviously is greater than 10, and the particle is trying to leave my system now, and I'm not okay with it. So what I'll do is I'll implement either of these particular boundary conditions. So I want you to look at these boundary conditions in isolation. These two were not simultaneously done. This is for one kind of system, and this is for another kind of system. So if my system is bounded with periodic behavior at the boundary or at the walls, then I'll only bother about these values. On the other hand, if my system is catering reflective behavior at the walls, I would only concentrate on this particular part. So I want you to separate these two particular systems. I want you to work on one system for periodic boundary condition and another system for reflective boundary condition. But just to make better sense out of these two systems comparatively, I'm bringing them in the same table. So at time t equal to 2, you have the particle which is evidently crossing the boundary of your simulation box. So I want to use periodic boundary condition. So I let this particle leave the boundary or leave the simulation box, and I would call another particle to take its place from other end, as you have seen in simulation in the animation of this periodic boundary condition. So instead of 12 being the x coordinate of my new position at new time step, I would take it as 2. So simply I have removed the box length from this, which means the particle has entered from another side into my box now. And if I am to implement reflective boundary condition, this has gone 2 steps away from the right side of my box. So I would kind of put it back into this box by creating a reflective effect. So I would insert it 2 steps to the left of the right boundary. So that would take it to x equal to 8. So, and when it is periodic boundary condition, as I've earlier mentioned, you need not really work on the velocities because particle, when it crosses the boundary or when it reaches the boundary, it doesn't have any effect on the boundary has no effect on the velocity of the particle. So velocity remains constant throughout the simulation if you are using periodic boundary condition. But if you are using reflective boundary condition, Every time you update your velocity, every time you update your positions when you encounter them with boundary conditions, you are also supposed to make appropriate modifications to the velocities. So I have to change the direction of my velocity because I have acted on this 12 value which is not in my simulation box. I've made it 8. So whenever I take change in x direction, I should also implement the direction of the change of direction in velocity along the x component. Similarly, in the next iteration, I have seen that the y component has also gone out from the system. So if I use periodic boundary condition, that becomes 1. And if I use reflective boundary condition, instead of 11, it becomes minus 3. Sorry, it becomes 9. So the velocity has to change from 3 to minus 3. That's the direction of velocity should also change because it is bouncing back after hitting the wall. So I want you to observe whatever I put here in the tabular form. The simulation I also want to give you. So initially my particle is at 8, 2. This is my initial position of the particle. And periodic boundary condition is represented with blue lines, and RBC is represented, that is reflective boundary condition is represented with this orange shaded point. So after at this particular time step, I have the position, that is it. And in the next time step, I have the position as 10 and 5 for both periodic as well as reflective boundary conditions. That is what I have represented here. And at this point, I have to decide on my system whether to go with periodic boundary condition or reflective boundary condition in the next time step because I'm crossing the boundary now. This particle is hoping to move out of the system and reach here. So at 12 and y being 8. So now if I use reflective boundary condition, instead of letting it out, I would kick it back into the system with reflective boundary condition. Or if I use periodic boundary condition, I would let it go out. So this is the particle which has left my system. And in its place, I would bring another particle from here, and that is this particle. So this particle has come from this side, and these lines that you see between these points are actually the displacements. The initial and final positions, they were not the paths taken by the particle. Well, in the next time step, this particle has went towards this side, and it has to hit the wall and bounce back. And as an evidence to this, you could also see the change in direction over here. There is a change in direction over here. Whereas this particle has come from here, it has left like this, and another particle came and took its position here, and this still has the same velocity, so it is trying to move out like this. And as it has moved out of the system, another particle has taken its position from the bottom. So this is a new particle which has come from the bottom image of our system. This is not a particle moving from here to here. This particle has left our system with the same velocity that it has earlier, and a new particle has taken its position from the bottom image. So this is it. And in the next time step, this particle has continued its velocity. See, initially it was given this velocity, and it is always trying to keep the same velocity no matter where it exists in the system. Whereas these particles were actually representatives of reflective boundary condition within the system walls. So because of that, this particle has gone like this and have come after bouncing to this particular position. And in the next time step, this has extended in this direction. This would continue in this direction until it encounters another reflection from the walls. And this would never change its velocity no matter what happens or where exactly it goes within the system. This is all about it. I want you to create a simulation using this particular box dimensions, or you can select any box dimensions of your choice. Take some initial velocities and position for your particle, and I've plugged two different simulation results into the same plot, but you can do them separately. You can create one simulation for periodic boundary condition, another simulation for reflective boundary condition, and when you do periodic boundary condition, make sure that you follow these steps that I have shown here in the flowchart. The logic is quite simple here. Everything that you do as per this logic would take you results like this. And I would expect you to actually go for more number of time steps or longer duration uh, study on single particle simulation. Yes. And now I also want you to have some insight on two particle system. So in single particle system, all you have is one particle. And if you have observed, the velocity of the particle is always kept constant. So that velocity was not changing because there is no other external force field acting on the particle, and internally also there were no other particles to influence the existing particle's velocity. But now when we take two particles in a system, these two particles would have some kind of interaction because these particles are real particles that we are accommodating in our system. And this particle, if it comes close to another particle, it would seriously feel the effect of repulsion between them. So whenever the particle separation distance is lesser, they would have repulsive force. If it gets much lesser, the repulsive force would be very much strong. And whenever these particles move little away or they separate, their separation distance, if it increases, then they tend to find some sort of attractive forces between them. And the larger the separation distance between the particles, the weaker it gets with the attraction forces that they experience against.
Can anyone else hear anything? My screen is blank.
Mine is also frozen. I can't hear anything.
I can't hear anything. I can't see anything. I'm
Yeah,
stopping the recording as of now.
yeah.
I'll restart it if when the picture begins.
Same